Modern processors are incredibly fast. They can execute millions of instructions every second, but even with all that power, poorly optimized code can still slow everything down. In this video, we will look at how ARM assembly code optimization works, and how understanding the processor's behavior can help you write faster, safer, and more efficient code. Unlike high-level languages, assembly code is not automatically optimized by a compiler. That means the responsibility falls on the programmer. Small decisions, such as which instruction to use, where data is stored, or how a loop is structured, can directly affect performance. Key optimization principles include minimizing instruction cycles, using registers instead of memory whenever possible, removing unnecessary comparisons, and ensuring proper alignment of code and data. Modern ARM processors use speculative and out-of-order execution to keep their pipelines full and avoid idle hardware. While a branch instruction is still being resolved, but the processor may speculatively execute the next instruction if the branch prediction is correct. The results are committed and performance improves. If the prediction is wrong, the pipeline is flushed and all speculative work is discarded, wasting time and energy. From the programmer's point of view, this behavior is invisible, but internally it affects cache contents, predictors, and power consumption. Processors can also reorder instructions and memory access to maximize throughput. Most of the time, this is safe and invisible. However, in multi-core systems, DMA operations, or when modifying control registers and memory mappings, instruction order becomes critical. ARM provides memory barrier instructions to enforce ordering. An instruction synchronization barrier, or ESB, ensures that previous instruction effects are completed before new instructions are fetched. Data memory barriers and data synchronization barriers ensure that memory reads and writes are observed in the correct order across cores and hardware units. Branch instructions are another source of performance loss, especially when predictions fail inside tight loops. To reduce this cost, ARM provides conditional instructions such as the conditional select or cell. Instead of branching, the processor selects a value based on condition flags. This avoids pipeline flushes, improves predictability, and often reduces power consumption. Optimizing assembly code is about more than speed. It's about understanding how the processor executes instructions, how it predicts, reorders, and speculates, and how memory visibility is maintained. By writing code that works with the hardware, you achieve better performance, lower power usage, and correct execution in even the most demanding systems.